but that's not what the question's asking. We're using a simulation method and determining the probability of selecting a red marble after 75 trials with replacement. So that's the trick to this whole thing, is that we're going to use a simulation approach so that we, for something that's very simple actually, so that we could learn the technique, so that if you're ever in a position where you can't find a formula to fit a particular situation, so you're given some kind of word problem, you know, you're given a scenario that you're just like, I don't know what formula this is for, or what formula is going to apply to this. What you could do is create a simulation and kind of discover the probabilities. This is really in lieu of, you know, like if a question said, what's the probability of getting heads when you flip a coin? I mean, you could flip a coin 10,000 times just to really confirm that about 50% is going to be heads. Or you can use the idea that there's two sides. But let's say you had no idea. Like, do you actually want to flip the coin? No. Would you rather let technology do that for you if it could do it faster? Now, if using technology meant that you had to sit there and watch technology flip a coin, heads, all right, flip another one, heads, you know, that's no better than flipping it yourself, okay, except you don't physically have to do it. So some of the apps in your calculators actually have coin and dice simulators, and if you actually played around with it, you can see the little coin flipping in the air. You're like, I don't want to wait for that. This does it pretty much instantaneously. All right. So in this case, we're talking about marbles, but the bottom line is it's really the same underlying concept, right, which I guess is the definition of the bottom line. So we have to design the simulation method first, and then carry out the simulation method using the calculator. So you can guess that on the test, it's not really so much the act of carrying out the simulation method that's going to be important, or as important as designing the simulation. Because people can fake random data all day long. And people try to do that. And then they're surprised when I catch them making up data. It's really interesting, because you wouldn't think, like, if you had, you know, like a random set of data, you're like, oh, I flipped a coin 10 times. You're like, okay, I didn't really do it in my calculator. I'm just going to write heads, heads, tails, heads, tails, heads, tails, 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 tails. You know, you do that for 10 outcomes. I'll write a note on your test paper, this is not random. And you'll be like, how did you know? You're like, I know. Statisticians always know. Anyway, so what we're going to do is define some numerical values to represent the 10 marbles in the bag. There's a test for randomness, by the way. That's how I would know, in case anybody's wondering. So I'm going to let 0 through 9 represent the 10 marbles. You can go 1 to 10. You can go 91 to 100 if you want. It doesn't matter, as long as they're 10 consecutive values. All right, 10 consecutive integers. All right, as long as you have that in play, then you're in good shape. All right, then one of these is gonna be the red one, and you could decide, because we're assuming that each of the marbles are the same in density, weight, etc. So the only thing that distinguishes one from the other is color. So they all have an equal probability of being selected. Right? We're going to assume that kind of relationship unless you're told otherwise in the problem. If I told you that the red marble weighed twice as much as the white marbles, then that would make it a completely different type of problem. All right? But I can choose whatever marble I want to be out of the 0 to 9 to be the red one. So I'm going to let 0 be the red marble. I mean, I could have let any of the values, but there's a particular reason why you would want to let either the lowest value or the highest value out of the set of possible values be the singleton, all right? So everything else, I mean, it's implied now that everything else is the white, but, you know, just in case, why not? Let 1 through 9 be the white marbles. All right, so what I would do is use a random integer function on my calculator, random integer, going from 0 to 9, and I would do that 75 times, and I would store all that into L1. All right, so just in case, I'm going to indicate what each of these things represents again. I'm sure it was covered, but you know, it was also last week. So minimum possible value, so min possible, maximum possible, number of trials, that sideways arrow is the store key on your calculator, STO with the sideways arrow. And L1 is L1. Right, we've been working with that enough that you should know where that is. To get to the random integer function, we select math probability option 5. It's not really so much the 5 that's the important thing, it's math probability. You want to know what menu you should be looking in order to find the relevant pieces of information. It's the math probability menu. All right. Once you get there, odds are you're going to be able to pick up what you need to pick up. You look at it and say, well, I need the random integer function. Well, I'll choose the one that says random integer. You know, when we get to combinations, permutations, you'll say, oh, that one looks like what it looks like in the formula, so that's the one I'm going to go for. All right, so math over to probabilities, so hit the right arrow 3 times or the left arrow once, select option 5. I don't know, hopefully they didn't change the settings on the TI-84 plus CE mega editions. Generally, it looks like this. Does it have a different display? It does? Oh, okay. So it's probably top to bottom what I'm about to write, left to right. All right. So 0, 9. So you just do 0, enter 9, enter. All right. Number of trials, 75. But I also want to store it into L1. For some reason on the older calculators, it didn't work if you closed parentheses. I don't know if that's true anymore. I do know that on this calculator it's not going to work if I don't close parentheses, but on yours it shouldn't make a difference one way or the other. All right. So it'll show you the values in the home screen. And again, these are random integers. All right. Hopefully that was discussed last time. Random integers means, well, whatever. The concept of a random integer is that it should be random. All right, so if I roll a die, I should get an outcome that may or may not be the same as the outcome that you get when you roll the die. All right, if we all got the same outcome, if we rolled a die, what would be the point? All right, there's no element of chance there. All right. Gambling wouldn't exist. Maybe that's a good thing. I don't know. So you look at my array of values and you say, well, I didn't get the same numbers as you. And I say, great. That's how it should be. You may look at it and say, because this has happened before, I got the exact same values as you. They're like, oh, well, that could happen too, because these calculators, I mean, they are programmed with the same initial values. So there's an algorithm that's used to determine randomization, and they all have the same initial random seed, right? It's an initial numerical value that's plugged into the algorithm, right? So if everybody turned their calculators on for the first time at the same time and ran this function the exact same way, you'd actually get the same numbers, right? So it wouldn't be really random in the truest sense of the word, but it would be random to you, and that's all we really care about, all right? So, and these are actually mathematically random, right? Mathematically random is good enough, right? So there's no actual discernible scheme on our end into where these numbers came from, right? Because, you know, like, believe it or not, perception comes into play even with randomization. What'll happen is if I were to say, you know, I do this activity in some classes, but if I gave you a piece of paper and I told you to, like in a magic marker, take your magic marker and draw 15 dots on that single piece of paper. You may think that you're going to do it randomly, but you're never going to be able to do it truly randomly, right? Because subconsciously, there's always going to be a scheme to how you plot those points, right? Me personally, I look at it as like the neglect factor. I haven't plotted a point in this area in a little while. Let me get one in over there. Just by making that decision, it's no longer random. Right? So if I say, you know, if I'm making up numbers, and that's how I know when people are making up data, because if I'm looking at the distribution of a roll of a die, let's say 1,000 times, or I'll keep it clean, let's say 600 times, people, like if they're making up data, they can't help themselves but to try to make it uniform. Make it roughly 100 values that are ones, roughly 100 values that are twos, and so on. But if it's truly random, you might not have a single one in 600 rolls of a die. If it's truly random, I mean, you could have 300 twos, and the rest of the values might be split up among 4, 5, and 6, with a couple of values completely disregarded. It's possible because that's what random is. Right? If at any point you're making a conscious or subconscious decision to include something just because it hasn't been included already, you're violating the laws of randomness. All right? So I have a random set of data, or at least as far as I'm concerned, a mathematically random set of data. It's random to me, and that's all I care about. All right? What I want to be able to do is sort this information out so that I can determine the probability of getting one red marble in 75 attempts. Now, we know that if there is one red marble and 10 marbles overall, the probability should be 1 in 10. Right? There's one that we want, there's 10 possible, and that's all there is to it. So I'm looking for around 7 or 8. Right? But if I get 2, that's fine. If I get 13, that's fine. If I get 74, that's fine. Very unlikely, but that's fine. Okay? If I toss this information because it says too far away from 7 or 8, then I'm violating randomness. Right? So how do we sort this? Very easy. We sort it. All right, so I'm going to hit Stat. In the Edit menu, which is your main menu, you hit Sort Ascending because the number I'm looking for is the lowest number in the data set. So I'm going to hit Sort A. And then I'm going to type in L1. Close them up. Close the parentheses. So sort ascending L1, and then hit enter, and it has sorted the data for me. Now, I actually, based off of this distribution, I really don't even need to go into the stat editor in order to find the values, because I can just count. I'm looking for zeros. 1, 2, 3, 4, 5, 6. I got 6 out of 75. You might say, oh, but I got 10. Yeah, it's random. That's fine.
It just says done.
Oh. That's because mine is like the high-powered, what you call it. Okay, so yours says done, so you're going to hit Stat and Edit, and you'll have the list of sorted data. Basically, you're just looking for the last entry that contains a 0, because we define 0 as the outcome of getting a red marble. And so any 0 that shows up is going to necessarily, because we sorted it in the ascending order, it would necessarily have to be in the beginning of the list. So I don't have to go too far to find all of my zeros. The 6th entry in my list is the last 0. All right. So the 6th entry. So for you, it could be something else. So you wouldn't write 6th if yours is like the 8th entry. 6th entry in, oh, that was quite the zoom. In my list is the last 0. Therefore, I have 6 out of 75 is the experimental probability. All right. So how do you distinguish an experimental probability from an ordinary probability? You really don't. So what we would just say is that's the probability of getting a red marble, but then we would make a note that it's experimental. All right. So in terms of just raw notation, P red means probability getting red. So how do you know it's in an empirical sense or an experimental or otherwise? In the theoretical sense, you don't unless you say so. All right. But if you're using a simulation, it's experimental. All right. This is a shortcut to avoiding actually getting 10 marbles, with one of them being one color and the other 9 being another color, and then actually carrying out this process. All right. With the added bonus of the element of randomization has been taken care of for you. Right? So you don't have to worry about like fumbling around in the bag to try to pull a marble out. Oh, that one feels familiar. Like the little gouge in one of those marbles. I remember that being the black marble. Like you don't have to worry about stuff like that because the calculator's handling it for you. So 6 out of 75. That's not the correct probability in terms of what it ought to be. What it should be is 0.1. Let me just clear this out. We're getting 0.08. All right, but it's not terribly far off from what the probability is. So our experimental probability is not too far away from what would be considered correct. So let me just show you something really quickly. If we have the number of trials is 75, then we have the probability of red being 0.08. All right. So that's just one thing to consider. That's what we just carried out. So what you might say is, all right, well, let me try that for 100 trials. I'm just going to do it very quickly. You don't have to do it with me, or let's just say you don't have to keep up. All right. If you want to just kind of enjoy the show, that's fine. So math, probability, option 5, you'd plug in your entries 0, 9, not 75, but 100 trials, store it into L1, close them up, close them up, then store it into L1. Enter, gives you that array of values. So then sort it out. So I get these values, and I don't really want to go into my list because I can do it here, so I'm just going to count them up. But if I had one of your calculators, I'd hit stat, edit, and then go see where the last entry containing a 0 was. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So with 100 trials, I actually got the 0.1. All right. So that's ultimately what I was looking for. Now, the idea behind experimental probabilities, you have no idea what the answer is supposed to be. Right here, we're just verifying something that we already knew. Like we knew it's supposed to be 0.1. So once we got it, we're satisfied. All right. under normal circumstances, you would be like, well, I don't know. Is 0.1 the answer? Is 0.08 the answer? I have no idea. So then you jack it up to like 1,000 or whatever your calculator can handle. That's the thing. Sometimes it says, yeah, no, I'm not doing this anymore. All right. So for 1,000 trials, I got 88 out of 1,000. All right. So then you'd say, okay, let me try 5,000 trials. And your calculator definitely can't handle anything more than like 900. So this is not something, or at least the older ones. I just did 5,000, so I'm just scrolling. Something in the neighborhood of 500 should be where it's at. $491. Let me see if it'll let me do 10,000. It's letting me do it. It's one of the reasons why I hate these graphing calculators now, because even though I've become an expert on them over the years, we're at the point now where it's such a waste, because even the emulators can do more than the calculators can actually do. I slipped and now I'm paying the price for it here. There it is. 950 out of, I think it was 10,000. All right, so this is, you know, what we just did initially, the black set there, the 75 trials, that was just showing one simulation. What we're doing now, or what I'm doing and demonstrating for you, is the experimentation method of finding a probability, right? Because throughout this process, yeah, we stumbled onto the correct answer, but we didn't really, if it were a really complicated probability question, we didn't really figure anything out until we tried it for an extreme number of trials. So what this would look like graphically, and I know everybody likes creating graphs. I'm going to get some decimal equivalents here. 88, well, 88 over 1,000. Everything's going to be in the neighborhood of 0.1. One too many. 0.088. Just bring it in a little bit. .0982. And about 0.095. So 0 trials. We're going to get out as far as 10,000 trials, and we'll scale everything based off of that. So 1,000 would be about right here, 100 would be about right there, 75 would be about right there. It's too messy to actually draw it in there. I mean, I could really, but it's not even going to be visible when I zoom out. All right, but I could put my benchmark here of 0.1. 0.08 is going to be just a smidge below that. 0.1 is obviously on it. 0.088, kind of in between. with the idea being that we're hovering around a particular probability. And so it's not really so much the fact that we're going to eventually stumble onto the correct probability as it is that somewhere in this curve, if I were to create a function out of this, somewhere in this curve, the probability would exist. So, you know, oftentimes, I mean, think of it this way. If we talk about the weather, if I tell you that the probability that it's going to rain is going to be 32.12589%, you're like, okay, cool. If I tell you that the chances that it's going to rain is going to be between 30 and 35%, I'm telling you really the same thing. You know, in terms of your understanding of the likelihood of it, I'm really telling you the same exact information. It's just one's a lot more precise. So what we're getting here, when I create this curve, is a neighborhood of probabilities. So these probabilities, that's a little thick on the curve itself, actually. What I'm giving you is an interval of possibilities. So the probability of red is going to be somewhere in this interval. Right? And that's really what it's all coming down to. Being able to narrow down the field of possibilities. Now, is that some recognizable function? Of course not. Right? All I know is that it's some kind of graph that's really just hovering around a particular y value, a p of x value. All right? And so once you kind of close in on the reasonable possibilities for a probability value, then you've really done your job. All right? And one of the focuses of one of the tech assignments that we're going to tackle is really going to be just evaluating that sort of thing. All right? Because really it's about long-term possibilities, especially with games of chance, because you want to be thinking like, what are the chances of winning or losing in the long run? But then you would also want to be thinking about immediate success. Right? So if I know what my chances are if I were to play a game for an extended period of time versus if I were only to play it in a short period of time, then that's going to be good information. So this is at a minimum what I would need, and then from there it could be try it for 5 trials, 10 trials, 20 trials. What is it approaching? What does your probability seem to be closing in on? All right. And I'll make sure that I don't think it was last semester. It was previous semester, where I had a good question that was kind of an example of what I'm talking about right now. I'll make sure that's available, along with the answer key, of course. All right. So this has been really kind of addressed in the previous question, but you can see the parameters have been changed a little bit. So 10 marbles are placed in a bag, 3 are white and 7 is red. What's the experimental probability of getting a white marble after 100, specifically 100 random selections from the bag with replacement? All right. So a key term here is the with replacement. So I'm relying on a lot in terms of what was covered last class. That is not the color highlighter I wanted. With replacement is telling us that the marble that was selected after a particular trial was replaced into the bag before a new marble was selected. All right. Same thing with cards, whatever, anything that involves with replacement, whatever was withdrawn from the set after it's been noted in terms of what it is, like Jack, Queen, 10, whatever, it's put back into the deck, reshuffled, and then a new card is selected. All right, same idea here. All marbles are going to be available at all times. Otherwise, there's really not much need for a simulation, because if I tell you that you have 10 marbles in a bag, one marble is going to be selected, and it's always going to be without replacement, you're only going to be able to pull 10 marbles. There's only going to be 10 trials, because after the 10th selection, there's no marbles left in the bag. All right. So these always, for these simulations, it generally has to be with replacement. All right. So 3 are white and 7 are red. So I'm going to let 0 through 2 be the white marbles. And I'm going to let 3 through 9 be the red. All right, 0, 1, 2, that's 3 values. And then same idea for 3 through 9, just count them up. This is like one little computational thing that I didn't know of until I became well, I'll say an adult, but until I became a teacher. Like if you're trying to find the number of values between two numbers, and I'm ashamed to say this, my wife taught me this. You have no idea how horrifying it is for me to admit that. So she asked me to tutor her in pre-calc, and she tells everybody to this day that I made her cry. Like, I couldn't help her to understand it. I made her cry. And so on a daily basis, she makes my son cry while she helps him with math. So I'm like, yeah, it's so easy, isn't it? But one thing, as you know, insurance, claims, analyst, lawyer, everything, the one little bit of math knowledge she had to offer to me was how to count values, the number of values between two numbers. I had no idea. I just always be like, oh, 0, 1, and 2, 0, 1, 2, there's 3 values. And I'm sure most of you know this. Largest number minus a smaller number, add 1. I had no idea. It blew my mind when I saw it. I'm like, you gotta be kidding me. So how many values between 9 and 3? 9 minus 3 is 6, plus 1 is 7. There's 7 values. I'm like, wow. And you know, it really sucked because during a test, I would be so nervous that I'd screw up something simple like that I'd be like, all right, how many values are between 1501 and 1700? All right, 1501, 1502, 1503. I wouldn't even take the chance. So just double check. That's the moral of the story here. The only way you can really screw this up is if you screw up the setup. Right? There needs to be 3 white marbles and 7 red marbles. So as long as your numbers carry across that idea, they have to be consecutive, but as long as they get across that idea, you're fine. So again, like I said before, it doesn't have to be 0 through 9. It could be 1 through 10. It could be 11 through 20. It does not matter as long as they're consecutive. All right? So random integer, 0 to 9, 100 trials, store it into L1, then we sort ascending, or L1. All right. But this time I'm on the lookout for 3 values. So again, math, probability, option 5. Depending on your display, it might look differently again, but it's still the same essential elements. And you'll find in a lot of cases, you'll be running the same computation. You'll just be using the numbers differently. All right? Because I did this when I did 100 for the previous problem. I used the same computation in the calculator. It's just what I was getting from it was different. All right? So stat, sort ascending L1. And again, yours says done. So stat edit. Now I'm looking for all the white marbles. So 0s, 1s, and 2s are my whites. My 30th entry is my last white marble. All right. And again, it could be different for you. Now, this worked out beautifully because it should have been 0.3, right? 3 out of 10. So I got an experimental probability of getting a white marble or quality E as being 30 over 100. But that, you know, and again, it's experimental probability. I wouldn't say that's dumb luck, because it is a significant number of trials. 100 trials isn't too shabby. You know, going back to the coin flip, if I tell you to come up with the probability of getting heads when you flip a coin, and you flip a coin 100 times, you're probably going to come pretty close to the true probability. It's only when you flip it like twice, and you come and say the probability of getting heads is 2 out of 2. You know, like that, yeah, no. You know, but 100 flips is not too shabby. So 30 out of 100, you're pretty confident. Now, if you got 29 out of 100, 31 out of 100, 33 out of 100, you know, then you're looking at it and saying, okay, it's in the neighborhood of 30 out of 100. I wonder if it's that nice, clean 0.3, 30%. You know, that's when you're prompted experimentally to say, well, let me jack this up to like 1,000, 10,000, 100,000, whatever. All right. And again, your calculator has limitations that mine doesn't. So I can go up. I mean, I just went up to 10,000. I probably could go up even higher. Most of the time, your calculator is given overload around 1,000 trials. All right. So with the newer ones, maybe it goes a little higher, but you know, that's when you want to get other forms of technology involved. All right. So number 5. Every semester, I rephrase this one to try to make it make more sense. And every semester I teach the problem, well, ever since 2015. I go through this problem in class and I realize it doesn't make as much sense as I had intended, and I go back to the drawing board. So we're gonna see, maybe this is the semester. I actually created a little tree diagram here to really try to illustrate the concept. Here, we're not gonna get the nice clean probability the way we got for the previous answers. Here it's just more about the simulation, right? It's about carrying out the process, because I want to be able to apply this concept to the game of baseball without having to actually play the game of baseball. For 2 reasons. 1, the economics of it. How do I get all these people together to play a game just to satisfy my curiosity? And 2, I mean, I could, I suppose, get a bunch of people that I know together to play baseball and try to go that route. But if I'm trying to use that to be representative of Major League Baseball, that's not going to end well. All right. Considering that when I was in Little League, I got sent down to the minors. All right. So I don't know if you know anything about Little League. Like, just so you know, that doesn't happen. It's not. They don't demote you. They sent me down to T-ball because I sucked so much at, like, I just couldn't hit. I had the worst case of the flinchies that was ever imaginable. So, like, the ball would come my way, and it was like, and, you know, to some extent, I still have it. Like, my reaction is like, so, the last straw was when they put me in like the farthest corner of the outfield, and there was a pop fly, and I settled underneath it. I'm like, this is gonna be my first catch ever. I'm like, this is great. And I put my glove up to protect my face. I mean, to catch the ball, and so I'm there, and I'm like, I feel like it should have hit my glove already. Why isn't it here? So I pulled my glove down to take a look. Boom, down, out cold. So, no exaggeration, all of that stuff happened. So yeah, I would not be a good representative of Major League Baseball. But I am interested in it because I'm very interested in people who can do things that, for me, might as well look like it comes out of the world of Harry Potter. Because when I see Major League hitters step up to the plate and somehow hit that ball, I'm like, one, I don't even know how you see it. For the first 10 years of watching Major League Baseball, I thought they were faking it. I thought they were just going up there and like guessing. And every now and then hitting home runs and stuff. Like I couldn't figure it. There's no way somebody could have this kind of skill. So I became increasingly more and more fascinated by it. So during a broadcast, this statement was actually made. So I'll read the prompt here. In 2015 baseball season, the population mean percentage of instances in which a team scores could depend on whether the leadoff hitter reaches base. Use the information below to design a simulation for whether a team scores at least one run in an inning. And so here's all the information. But the graphic came up and the Mets announcers were talking about it. I feel like they were talking to Sandy Alderson, who was the general manager of the Mets at the time. And in the conversation, this statistic came up. It was, if the leadoff man gets on, statistically, they collected the data, 57% of the time, that team will score at least one run in the inning. All right? And I was fascinated by that because it's so open-ended. You could have one run, because at least one means one or more. You could have one run in the inning, or you could have 20 runs in the inning. But just getting that leadoff hitter on makes it more than a 50% chance that you're going to score. All right? And you'll see when we get into the games of chance, when we start talking about roulette and like tech assignments and stuff like that, that sometimes in order to make a game unfair but in your favor unfair, all it takes is just knocking it off of that 50% probability, even if it's just a smidge, because you're looking for long-term success. And nothing exemplifies that quite like baseball, because the number of at-bats an individual has, 300 to 500 per season on an individual level, 162 games throughout the season per team. So it's a large sample. So it is the perfect game to talk about long-term outcomes, right? So you talk about like a pitcher, for example, who throws 98 miles an hour versus one who throws 94 miles an hour. You're like, well, I can't throw 60 miles an hour. So both of them are like really, really awesome. But the 98 mile an hour one has something that the 94 mile an hour one doesn't. That extra velocity in the long run gives them the better outcome. All right. So what we want to do here is, and you can apply that to whatever your favorite thing is. It doesn't have to be sports related. It doesn't have to be baseball. Find the thing that you like and see how you could apply this. There is a statistic out there. So the average on base percentage for all major league teams in 2019. All right. So I kind of refreshed the data a little bit. The comment was made in 2015, which is when the Mets went to the World Series last. It was a good year until the end, when we didn't win it all. But I collected this data from last year. The team gets leadoff batter on base in a given inning. Our possibilities are yes or no. So that .323 on base percentage is a probability. So the yes is .323. The no is the other .577. All right, I know it's hard to see, but it's in there. All right. Then, once you've established whether the leadoff hitter is on or not, now it's a matter of determining whether at least one run was scored. All right. And you can actually simulate a game, but it's, again, there's that gray area. At least one run. Did they score one run, or did they score 10 runs? That's a little iffy. But our possibilities are, if they got on base, now you have a 57% chance. It's like you're on base, now let's go to work. You have 57% chance of scoring a run versus 43% chance of not. All right. If the leadoff hitter is not on, and this was the other statistic that was given, you only had a 16% chance of scoring at least one run. All right. Now again, it could be one run or 10 runs. If that 16% of the time you knew you were scoring 10 runs, well, I'll sign up for that, I guess, versus 57% of the time only getting one run. So it's like feast or famine, but I'd rather, at least go for it here. But we're looking at 16% versus 84%. All right, so the simulation here is actually pretty much already done for us. We just have to spell it out in terms that the calculator could understand. All right, so my first layer here would be whether or not the leadoff hitter got on. Put a little question mark there. All right, so we're looking at decimals to the nearest thousandth. So that to me means that we should be working with 1,000 values. All right, so what I'm going to do is let 0 to 999 represent all possible outcomes. All right, so the little sub-layer to that would be that we would let I'm just debating now. Let me change that. Let's make it 1 to 1,000. Just so I could actually use the percentages that they gave us. It'll be a little cleaner, I think, in this one case. So 1 to 323, because that's 323 values, would be the leadoff hitter getting on. So since the question here is leadoff hitter on, I would say this is our yeses. And so 324 going out to 1,000 would be the case of no. Now this is a conditional probability, so it's unfortunately not the kind of situation where, well, fortunately or unfortunately, it's all relative. I couldn't do multiple trials like this unless I was only concerned with whether or not the leadoff hitter got on. I want to know if the leadoff hitter got on, what is the outcome after that? All right. So the next layer to this would be the condition if the leadoff hitter is on. Did at least one run score? All right. Now here it's out of 100 because those probabilities are actually represented out of 100. They were given in percent forms, percent, the cent being 100. So I can go with a little simpler of an approach here. Let 1 through 100 be all possible outcomes. And 1 through 57 would be my yeses. And 58 to 100 would be my no's. All right, but the third layer, well, the second layer, the second part of the second layer. It's a lot of layers. If the leadoff hitter is not on, so if the leadoff hitter is not on, did at least one run score. And so it would be the same framework. Let 1 through 100 be all possible outcomes. but this time it was 1 through 16. Would be my yeses. And 17 through 100 would be my no's. Taking the time to come up with the parameters initially, a good setup to your parameters, that's the key to everything. Because now the rest of the problem is going to take care of itself. Because the first thing I would have to do in my calculator would be a random integer going from 1 to 1,000. Then a random integer going from 1 to 100. This whole setup here is telling me what I should be on the lookout for. All right. So the question was, use the information below to design a simulation for whether a team scores at least 1 run in an inning. And so we've accomplished the goal. That's all the question was asking us to do. Right? Because, I mean, there's still that variable in there of at least 1 run. What is at least 1 run? 1 run or 30 runs, So that part of it, could go in a bunch of different directions. But what I could do, just to get a sense of it, would be to just carry it out for a trial and see if I get an answer that makes sense. All right, so math probability option 5, 1 to 1,000. All right. So what I just learned from that is that my leadoff hitter is not on. So if I follow the tree diagram, I'm in the bottom half. Now it's a question of, okay, well, the probabilities that were given to me leads me to think that it's probably not very likely, only 16% chance now, of scoring at least 1 run. So I would run my random integer, math probability option 5, from 1 to 100. We don't need to store it anywhere because it's just a single random integer. All right, 89. All right, my yeses. So we're in this category here. My yeses are in the 1 to 16 interval. I just got an 89. So my leadoff hitter did not get on, and I did not score at least 1 run. All right, which kind of fits what you would expect. All right, so then maybe try it again. 685, leadoff hitter did not get on. Did not score a run. All right, so if we're in the 324 to 1,000 for the first random integer, that would be the leadoff hitter not getting on, which puts us into this category here. It's all conditional. I'm looking for 1 to 16 to show that I'm at least getting a run out of this. I didn't get the leadoff hitter on, but maybe the second guy up got on. And then the third guy up hit a 2-run homer or something. I don't know. But it didn't happen. I get the number 28, which puts me in this category. Let's do it one more time. 637, leadoff hitter on, not on, didn't score. I was actually about to say I'm going to keep doing it until I get the leadoff hitter on. I got the leadoff hitter on. 44 falls into the first category here. So leadoff hitter is on. Now I have a 57% chance. Better than a flip of a coin. So let's see. 11. So I'm in this category here, 1 to 57. 11 does fall in that category. So I scored at least 1 run. All right. So what was it, 2 or 3 times I didn't get the leadoff hitter on, didn't score anything. But the one time I got the leadoff hitter on, I got at least a run out of it. Right? It could be a big inning, or it could just be 1 run. But it's at a minimum, it's helping to gain a little bit more insight into what Sandy Alderson was talking about in that broadcast. And so, like I was saying before, it maybe you hate baseball. Find something that you do like. People talk about percentages all the time. You know, like you hear it in political dialogue, you hear it, you know, the radio, you hear it, it's like blank percent of this, blank percent of that. And it's like, they're clearly trying to convince you with their knowledge of percents, you know. Use this to poke some holes. You can run a simulation on what, you know, like what their claims are and see if it's actually fact-based, right? Because generally, it's almost always going to include some kind of bias. So, when I was talking about before, that idea of, you know, you not truly, without the aid of technology, not truly being able to develop randomness, the idea there is that if there is the absence of randomness, there is the presence of bias. Bias is the presence of some underlying scheme in assigning values to data, selecting values, selecting individuals to be part of a study, whatever it is. If there's an underlying scheme to how those values are selected, that is the introduction of bias, right? And so generally, if we can show what a situation would look like if it were truly random, then that gives us a benchmark. And so anything that deviates from that would necessarily not have to be random. Right? So if somebody's saying that they're unbiased in their approach to anything, you could think of it in terms of, you know, games of chance, you could think of it in sports, you could think of it in race relations, whatever you want. If they're saying they're unbiased, right down the middle, then they're saying it's all truly based on random selection. So you can determine what random selection looks like in terms of a simulation, and anything that deviates significantly from that wouldn't necessarily have to be biased. All right? And so it's a very powerful tool if it's used.